Hello, good morning, good afternoon, good evening to all of you, and thank you so much for joining today. And without I'm Jitendra Sharma. I will be the host for this particular session, and the Kamal is also will be assisting us throughout the session to speakers and attendees if they have any issues. Without a further ado, we are pleased to welcome Amit Geynis, a security researcher and team lead at PlaxidityX, formerly August Cybersecurity. Amit specializes in automotive embedded security, penetration testing, and the vulnerability research with prior experience at IBM's Cybersecurity Center of Excellence and the Broadcom, as well as uh, leading a signal research team in the IDF Cyber Intelligence Unit 8200. Amit brings extensive expertise to his role. He holds a BSc in Communication Systems Engineering from Ben Gurion University. Amit will present tales from a penetration testing team, insights on recent zero-day automotive vulnerabilities. This talk will explore real world zero day vulnerabilities discovered in automotive systems, including TCU, BCMs, and safety critical components. Amit will detail four specific uncovered vulnerabilities by his team, offering insights into the complexity of these issues and the sharing lessons learned and the strategies for effective mitigations. Please join me in welcoming Amit Geynis. Amit, over to you.
Thank you, Jitendra. Um, hi everyone. Good morning. Happy to be here. Um, Again, my name is Amit Geynis. I'm a security researcher and team leader, part of the penetration testing teams at PlaxidityX, formerly ours. And today I'm going to share with you this talk that is simply called Tales from a Penetration Testing Team. Our penetration testing team receives and reverse engineers many ECUs from our clients, such as TCU, BCMs, instrument cluster, radars, airbags, and other safety critical systems. We find zero-day vulnerability in all of them. Some are very easy to exploit, some are harder, some have very complex software bugs that developers can easily miss, while others should have been caught during a standard security review. We believe that by sharing insights from vulnerabilities that we have discovered in production components, our colleagues across the industry can get a better understanding of the types of vulnerabilities in vehicle code or configuration and build effective strategies for mitigating the risk. So in this talk, I'll present four distinct zero-day vulnerabilities found in four different OEMs via four diverse communication channels. This will give you a representative view of the complexity and variety of security issues encountered by our team in recent years. These vulnerabilities are found pre-SOP and already fixed and by the responsible parties. But please keep in mind that some of the details were redacted to ensure the confidentiality of these involved parties. I will conclude with a lesson learned and how best to mitigate and avoid such issues. So without further ado, let's start with our first vulnerability. Vulnerability number one is a global buffer overflow to achieve full control of an AutoSAR ECU through CAN network access. So the attack model here is an attacker that is able to send frames to the target ECU via the CAN network. So our vulnerability starts, just like many other vulnerabilities, with a mem copy. And this mem copy is copying our own 64 bytes of data to somewhere in memory. That somewhere in memory, let's call it some PTR. Well, It's turned out that this sum PTR is pointing to a buffer of size 32 bytes, smaller than the copied data. So we have a classic buffer overflow. So we wanted to look what exactly is found past that buffer. This is the next stage of an attack. And it turns out that the same sum PTR is actually located after that overwritten buffer. So this gives us a very powerful primitive because we are able to overwrite the pointer. So the next time this memcopy will take place, we are controlling its destination. And if that's not enough, the entire vulnerable code is running as part of an interrupt service routine. And that effectively means we are running in supervisor mode. It means that we will not have much obstacles to get full control of the device. So to quickly summarize the steps here for this vulnerability, we can send one frame that will override the pointer, for example, with Café Café. The pointer is now overwritten, and it's now pointing to somewhere else in memory, which is Café Café. The second frame that we are going to send is the BIF, and that BIF will be copied to Café Café. Note that a third frame that will be sent will be copied to the same place, Café Café, and will override this previous dead BIF. So this means that this is a write everywhere primitive, but only once. So to conclude this vulnerability, vulnerability let us use an arbitrary write via kind of the message, and then we use that to write directly to the return address on the stack. This bypass the stack canaries in the system and also a CFI that monitored indirect calls only. Then by using return-oriented programming, we can hope our way to get arbitrary code execution. So this was a classic and simple vulnerability, which leads to a remote code execution over Canvas. Now to our second vulnerability. Our second vulnerability, in this case, our target was the communication stack of an ECU connected to the in-vehicle Ethernet network. So like before, TACModel here is an attacker that is able to send some frames to the target ECU via the Ethernet network. We started by using our interface fuzzing tool to fuzz the some IP service discovery protocol. It's a well-known automotive service-oriented protocol. The fuzzer sends many bad and malformed packets to the target and monitor the target for a crash. And the fuzzer successfully crashed the system. The system outputted a crash dump. We analyzed it, the crash, and we saw that the stack overflow caused the program counter to point to an invalid memory area. And note that there were no stack canaries added to the vulnerable functions. We discovered that this vulnerability only gives us control over the 3 least significant bytes of the program counter, meaning that no matter what value we will inject to it, it will not be a valid memory area, or will always be this FF byte on the MSB. So no full control on the SD task. So not giving up yet, we also fuzzed another protocol in the same system, the IPsec protocol. And once more, the same thing, another crash. We also don't need to be authenticated. because the crash is happening as part of the authentication process in the IPsec. And again, no stack canaries and the vulnerable function. Okay, so now in this task, we do have full control of the program counter, but is it hacked? The next stage is to ask ourselves, can we get control on the safety critical resources of that ECU? And we were blocked trying to influence those resources. So the task with the IPsec implementation did not have the permissions for the safety critical resources. So what do we have here? A full control on a task with a limited permission and limited control on a task with full permissions. So yes, the service discovery task did have the permissions. So we needed to go back and see what is limiting us. And the limit is rooted in the Ethernet MTU limit, which is 1500 bytes per frame. So on first look, it seems like we cannot bypass it. But there is a way to send more than 1500 bytes, just not directly over the Ethernet interface. By using an internal socket, we can send up to 8 kilobytes per frame. So by using the IPsec vulnerability to control its tasks that did not have the permissions, we can then send a frame using internal sockets between the tasks, leading to full control over the service discovery task as well. So by using the union of these two limited vulnerabilities, we have full control of the safety critical resources of this ECU. To our third vulnerability with shaky cryptography. In this setup, we had a TCU that can send instructions to the BCM based on remote commands received from the backend, and it's triggered by the user mobile app. These instructions are validated through a unique pre-shared key and using AES in order to prove they came from a valid TCU source. And before talking about the specific problem here, let's talk about the typical problems we encountered when using or seeing cryptography implementations. So the first is non-random values. Sometimes they are just constant values or using a constant seed and are repeated after reboot. Derivable keys, meaning they can be easily and directly calculated from eavesdropping on the communication, and no need to break any AES for that. Get or set key functions. Sometimes these are debug functions left open or some other bad logic. In one case, we had a get key function that was implemented in HSM instead of keeping the key inside and just returning the HMAC. Hard-coded master key, so a secret that is shared by all the fleet, and it is hard-coded in plain text in the firmware. Easily disabled. For example, if the HMAC is all one, just pass the check. Brute forceable keys, so if the key bit length is too short or derived from a smaller set of options, this is brute forceable. So what did we have in our setup? So because of a faulty design, just by eavesdropping to the communication at a specific time, we could easily calculate the key. But this not enough. We also had it also implemented a get key function. So we don't need to just eavesdrop on the right moment. It's also so you can just get the key in this way. It also had a set key function, but for using that function, you needed a master key. And of course, the master key was plain text, hard coded in the firmware. So by using any of these above vulnerabilities, we were able to bypass the validation and impersonate the TCU without any prior knowledge of any key materials. To our last vulnerability for today, a remote and persistent vulnerability via cellular connection. In this setup, we had a TCU with a cellular modem connected to a safety critical canvas. The TCU communicates with the backend via secure TLS connection and can also receive a binary SMS to trigger communication with the backend. Zooming into the implementation, the TCU has a TLS client for the TLS session and some SMS client for the SMS messages. And of course, the TLS session is authenticated and the SMS channel is not. These clients forward messages to a message parser module, let's say type A messages from the SMS and type B from the TLS. And probably at this point, you can probably guess what an attacker can do. An attacker can just send type B messages via binary SMS, and the parser does not distinguish between the channels. So we had a nice secured TLS gate, but also an SMS channel to bypass it. The next step of an attacker is to use the implemented backend commands. And the backend can replace a file within that system. We investigated the file system, and we saw that some files were tagged with a digital signature. If they were replaced, you will get a kernel panic, and the whole system will restart. But some of the partitions in this file system did not have any validations, and subset of those were not flagged as non-exec. So therefore, an attacker can inject arbitrary executable to any of these partitions. Exploiting this vulnerability, we were able to replace a file in that system, and that enabled us to run a full demo of injecting canned messages from our location in Tel Aviv, Israel, to impact the vehicle of the client located in Europe. So for conclusions, our penetration test demonstrates that high severity zero-day vulnerabilities are still common in multiple types of ECU, and some are safety critical. And more and more of these vulnerabilities are now caught pre-SOP nowadays because the industry is investing much more in security, which is a good thing. These vulnerabilities are the result of faulty implementations of protocols and interfaces exploitable via CAN, Ethernet, or cellular connections. Moreover, these vulnerabilities are not unique to new automotive protocols like SAMAPI, as we saw, but also, are also found in network using traditional protocols like IPsec. Our finding reflects flaws in the product development process as well as lacking security design. We believe that the security of modern complex vehicle system requires a holistic approach with layered security controls and fast security auditing. Augmented security awareness during the development process could have helped detect at least some of the issues we discovered in the early design and validation stages. For example, conducting an initial secure design design review for the security sensitive process to detect logical security faults in the initial design process. Another interesting takeaway here is that fuzzing tools can be very efficient in detecting zero-day vulnerabilities and may be deployed in early validation stages to harvest the low-hanging security fruit. Don't underestimate limited security issue. You can't know how and when it will be exploited in the future. You probably already know that, but hardening is crucial. Using stack canaries, CFI, properly configured MPUs, ASLR whenever possible, and also on a higher system level, EE architecture with network segregation is important. And then penetration testing based on the labor-intensive manual code reviews, reverse engineering should be planned after all the other validation steps to catch the more subtle faults that would otherwise be missed. We hope that more players in the automotive industries will disclose such vulnerabilities. This shared knowledge will help us all learn from each other insights and create a better and safer production environments for connected vehicles. So thank you. You're invited to ask questions.
Thank you so much, Amit. It was really wonderful session and a lot of insights. Audience has a lot of questions to ask. I will take one by one, as many as possible we can take. Let me start with this one. Do you see the automotive security landscape learning from their past mistakes, or are these vulnerabilities bound to be repeated forever?
So hopefully, in the end, the things are improving and improving. So for sure, we can see in the recent years, as I said before, the industry is cutting these vulnerabilities more and more pre-SOP nowadays, which is like a good thing. But yeah, the vulnerabilities will always be there. You just want them to be to take more time to find them for an attacker, and then if there is alert security controls, an attacker will not just need to find one vulnerability; he needs to find a chain of vulnerabilities, and the point is to make an attack take a lot of time and resources to facilitate such a. Yeah.
Thank you, Amit. We have another question. Do you use open source fuzzes, or it's proprietary software?
So it depends on the method. When we are talking about fuzzing, there is white box fuzzing or black box interface fuzzing. When we are doing the white box stuff, yeah, it's open source tools for that. But as you may know, white box, it's not usually an easy thing or something that is possible. It depends if you have the source code and you can, or the binary and stuff. Sometimes you don't have it, you just have the ECU. Sometimes the systems that they are running is complex to integrate this kind of white box fuzzing, and it also requires someone with experience, with knowledge to do that. and knowledge about the functions inside that you want to fuzz. So we saw that if we want to go to a scale approach and get people that are less experienced also to running stuffs and get something plug and play. So we are developing our own black box interface fuzzing and also like dynamic security testing. So it's not just fuzzing. You can test for things like sending a reset command while driving to an ECU. Is it does it accept it or not? It's things that are not necessarily fuzzing, and everything you can develop as a internal thing. But yes, we also selling these kind of tools.
Thank you. We have next question. How do you typically identify this kind of vulnerabilities in the first place? By extracting and reversing the ECU software or by fuzzing the CAN bus messages?
So it depends on our clients. So we are part of a process in the end, and it depends on the client's willingness to provide. For example, if we can provide a source code, then we can do a source code review. So we can go in that option, and or it can just provide binaries. So it depends if it's like a white box, let's say, a project, or it can be a black box one when we get just an ECU. So we can, on like the first level is, yeah, we can do fuzzing, check for debug interfaces, and try to extract the firmware in this way. The JTAG is open, etc. And sometimes it's more complex stuff. Opening it's trying to extract external flash from the ECU and read it, or bypassing a JTAG block. We can talk about fault injection, for example, to bypass some hardware checks and extract the firmware from this way. So yeah, in the first step of an attacker trying to get a remote code execution is to get the software somehow open source, or firmware extraction. Yeah, and reverse engineering, of course.
Okay. Thank you. Next in the line, interesting one. How can quantum computing be used to break existing cryptographic algorithms? Any idea on this?
Yeah, sure. So we all know that quantum computing is advancing, and some of the cryptographic algorithms used could be breaked by quantum computer. Uh, so and there is a ongoing process also by NIST to introduce this quantum secure algorithms. So when you are developing new software, you need to think about the life of a vehicle. If it's 25 years on the road, in some point, quantum computer will be able to break these cryptographic algorithms. So you need to think about how you can either introduce these quantum secure algorithms, or in an update, do you just need to update your software, or the hardware can support a future update to another algorithm. So yes, you need to take it into an account for the future.
Thank you. Another question. Uh, when you are testing and trying to gain access to safety critical software, does that include powering down the vehicle, preventing it from driving? Where I live, where live a white vehicle breakdown can also cause death, isolation, whether not just a crash. So, how do you respond to that?
Um, So the when we are doing penetration testing, it's we can split it to two parts: a component penetration testing, and then it's not a vehicle. We have an ECU on our desk, separate one. We can simulate the other ECUs for that, but basically it's pretty safe. And when we are talking on system level penetration testing, we're doing it on when it's ordered by a client, so it will be on site on in a place that it's capable of doing this test. And of course, when you get to a point when you need to do some testing while driving, you need to be aware of these things that can vehicle breakdown can cause stuff. So it happened in the past that we broke an entire vehicle just by sending some fuzz message that all the vehicle went bricked, and it was needed to be towed back. Um, so this sometimes happen when you research stuff, but you always, if you are doing driving, you will always do it like slow speed and in a place that is designated for this kind of testing. And if it's a black box penetration testing we are doing here, so we are doing quite the same in our premise.
Thank you, Amit. Next in line, we have how important are hardware-based attacks, glitching, side channel, etc., for your work in finding vulnerabilities?
So the importance is first to be aware that it is possible. So it's not enough to just say, okay, my JTAG interface is locked, so no one can read the firmware. So how an attacker can get my firmware? So you always assume that the attacker will have access and can get the firmware in some point in time. And then you need to, from that point, you assume what are your defenses, how you harden your software, how the whole system is hardening with the EE architecture. And of course, when you do a secure, you invest in secure coding and secure code reviews, penetration testing. It's important, and we are time to time we are requested to do some kind of this fault injection by power glitching, etc. If it's needed to prove something that it is possible, so we do that. But if the hardware is not stating that it is safe for that, like hardware security models or something, you can assume that it is possible, and you don't have to do that to prove that.
Thank you. So I think I have covered in Q&A all the questions, but wait, in the chat box, a lot more questions are there. Let me start to take one by one. Uh, okay. Any automated tools used to find vulnerabilities? So I believe Rajesh is asking a specific tools name, something.
Yeah, so as I said before, besides things like white box fuzzing with AFL++, we are using our own development for we found that there is a lack of tools that will be comprehensive and complex enough to do security testing for specific automotive use cases. So you can look it up on PlaxidityX auto tester, but this is what we are using internally.
Thank you. Another question we have, any commonly found vulnerabilities in secure boot feature?
So yeah, sometimes we are reviewing secure boots, and we can find some issues there. Sometimes you can, when you're writing a secure boot software, you need to pay attention to fault injections also. So things like checking, reading something from a place that can be glitched, you can do it multiple times, read the same value to make sure that you read the right value and make the attack process more complex. Uh, so this is one way to look at, and but in the end, secure boot does not protect you from runtime vulnerabilities that are the most common. So secure boot helps you um, to defend against persistent threats that will be there. But as the case that we are seeing, that most of vulnerabilities are kind of a runtime. Most of them are memory corruptions. So and you can, and once you got control of an ECU, you can get it stay alive, running on your battery until the time that you want to uh, do the actual attack. So secure boot is important, but it's not sufficient.
Thank you, Amit. One last question we have is the TCU located vulnerabilities can be exploited remotely from the first place? Means like, can it be exploited remotely?
TCU. So I don't think I understood the question, because as I showed before, the in the fourth vulnerability we did it remotely. So from another continent we send an SMS, and we got control of that TCU. We then sent a canvas messages to show up on the dashboard, and so yeah, so remotely it's possible. So if I can send a canvas, then I can influence safety critical things on the vehicle. Or maybe the attacker will want to hop to another issue from there, who has a second vulnerability, and do a lateral movement. I hope that answered the question.
Thank you, Amit. Just to note for the audience, Amit is agreed to provide some time on the launch area. So please feel free to reach out to Amit, talk in person, discuss, get your queries answered. And with that all, thank you so much, Amit. It was really useful, a lot of practical exposure, and a lot of insights we have received from you. So we really appreciate your time and efforts. And I appreciate the time from audience as well. Thank you so much for joining and for all the emojis. Have a good time and good day.
Thank
Keep
you.
enjoying the
Have a nice
conference.
day.
Thank you.